So in this project we can visualize the graph algorithms. It's the graph algorithm visualizer. We can visualize the pathfinding algorithm, minimum spanning trees, and topological sorting. Examples of the pathfinding algorithms that we can visualize is depth first search, breadth first search, Dijkstra, the uniform coast search variant of it, Bidirectional BFS, Bi-Directional Dijkstra, A star using the Manhattan heuristic function, Greedy-BFS first using Manhattan distance heuristic function, A star, Greedy-BFS first in bidirectional manner, as well as A stars. And we can animate random mazes or anything random spanning trees, and yeah, so let's try one. Let's get Recursive Backtracker. Okay, so now we have our start and our end, and what we can do is let's for instance try the bidirectional breadth first search. So let's do that. Let's change that to bidirectional A star, and let's try it out. As you can see, they are both searching for each other until they find an intersection node. And they found an intersection node. Now the program tells us that yeah, you can drag start and end to see how the path is affected in real time, instead of it being animated. So let's get that here. Let's try it to get that here. As you can see, the path is being modified as we go. So that's the result if end was there or start with there was there. Another thing we can do is let's clear all of that. Another thing we can do is we can build our own walls. So let's try a breadth first search here. And it found the shortest path. Still we can drag end and start to see how the path would be affected in real time. This is all written in vanilla JavaScript. And yeah, we can also decrease the cell size, which is the node size, make the grid bigger or smaller. Okay, that does some interesting stuff. We can still use the real-time versions of mazes. Let's try Greedy-BFS first Manhattan. So yeah, it found it, and that's the path. We can still drag it, drop, move it around, see how the path would be affected in real time. Another thing we can do is we can add weight node, which is beneficial if you are using Dijkstra, which finds the shortest distance to a node, meaning the lowest weight to reach that node. So let's try that out. Clear all, and let's try Dijkstra, and we can build the normal path would be from here to here. So let's put some weights to make it go on top or from here, to see how the path is affected. So let's do Dijkstra. See how it got to the node without taking the weight nodes in the path, because it's larger weight than the this weight. So yeah, that's how you can view Dijkstra, how you can see how it chooses the lowest weight and all of that. So let's try to visualize it again without the weights. It would take the path to here or to here. So yeah, just like I said, and yeah, we can play with that, see how the different algorithms work, how they search the search space, how it's actually working, not just like conceptually, but you can see that. Minimum spanning tree. Minimum spanning tree is a tree that connects all the vertices in the graph. It's a subgraph that contains all the vertices without cycles, but has v-1 edges, and it uses Euclidean distance for the edge weight, and that spanning tree should be minimum, where if you add all the edges costs, it would be minimum. So yeah, let's try that out. As you can see, it tries to connect all the nodes together without taking a route that is of a more distance or of a more weight than the one before it. So really connecting all the nodes in the least distance. So yeah, that's pretty fun to watch. Each time you click the Prim's algorithm, Prim's minimum spanning tree algorithm is computed, so you always get the minimum spanning tree. You can also remove nodes by right-clicking on them to see how the minimum spanning tree is affected. Another thing you can do is you can generate random networks to see how the minimum spanning tree is affected on a large number of nodes. So yeah, that's cool. Topological sorting, it's a method to sort tasks where it sorts the path on in degrees, where it sorts the nodes on in degrees, and it's only applicable on directed acyclic graphs, and it uses Kahn's algorithm. So let's say task 1, its prerequisites is 2 and 3. 3, its prerequisites is 4 and 5. So let's visualize that, and yeah, it tells you 2, 4, 5, 3, 1. You can do 2 because it's not dependent on another task, 4 because it's not dependent, 5 because it's not dependent, and when you finish 2, 4, and 5, you can do 1, and when you finish 1, you can do 3. Okay, so that's that. You can move that around, see what happens, and to view that topological sorting doesn't work on cyclic graphs, because, well, if we add 1 here, then 1 would depend on itself. So let's try to visualize it. Fail to do topological sort, there exists a cycle, and you can view it here. Okay, so that's the project. It was a pretty fun one to do, and yeah, I understood a lot of stuff out of it, and yeah, that's that. How it works is basically, well, we can see that. So let's try to view the DFS version. Well, we have a DFS version. Okay, the DFS version, I mean. It does the normal DFS traversal, but each node has a div reference where all of these nodes are divs. Okay, so it has the div reference, and it adds a class of CSS that changes its color and do the animation, and disables or enables buttons on pressing, and it set times out to 10 milliseconds, calls itself again with the new values of parent map, choice current, and all of that, like a normal while loop, but with a set timeout interval. So yeah, it keeps calling itself to construct, to do something like a loop construct until it's finished, whereas the lengthy stack would be empty. And this the real-time version of it is the normal depth first search traversal, but without animation and with a while loop instead of a set timeout. And when we drag and when we drag the start and end, the real-time version is the one running, and when we animate, the non-real-time version is the one being run. So yeah, that's the project. It was pretty fun to do, and it's live on my GitHub pages link. I would provide the link in the description in the post, and yeah, that's that. Have fun playing with it, and yeah, thank you.